Up till now, we have seen discrete memoryless source, that is a source which emits discrete messages. This we have seen. Okay, so this is a discrete memoryless source. What is the meaning of discrete? See, these terms are very important. You'll have to understand these terms. What is the meaning of discrete? That it is not continuous. It has finite size. And memoryless means that one, if we get x0 and then we get x1 and then we get x2, then x1 is not dependent on x0 or x2. This is the meaning of memoryless. So we had discrete memoryless source. So what we did encoding, source encoding. This was our source encoder. We added certain redundancy so that if there be any error, if there be probability of error in this, then we are able to retrieve the original message. So from discrete memoryless source to source encoder, we have seen up to this, and the algorithm that we have seen is Huffman coding. So through Huffman coding, we achieve what is called prefix codes. This we have done. Now, the output of this, let's say it's x, where x is, we write like x0, x1 up to, let's say, xj. Okay, so this is the x alphabet. This is the way we say x alphabet. So from this x alphabet, what we get? We get these symbols. And there's one term called cardinality of the alphabet. Cardinality means the number of elements present. For example, here we have j plus 1 number of elements. So to make it j number of elements, let's say this is up to j minus 1. Okay. So this is what we are getting from this point after our source encoder, not from here. Maybe this was the average entropy, here was hs. We added certain bits to it in a binary channel, in a binary system, and then we got this x. This you understand, we have done this. Now, what it will go through if it has to reach the receiver? For example, we are transmitting it, then at the receiver we will receive this thing, what we are sending. So what it will have to go through? It will have to go through the channel. Even in analog systems, for example, if you have a radio transmission, we have radio stations transmitting radio signals in megahertz and kilohertz. The channel is air. Then we have telephones. The channel is copper cables and then optical fibers. So it's a mix of so many cables. So these are channels. It can be air, it can be optical fiber, it can be copper cables. So let's say we are talking of digital communication. So this is channel. What we call the way we call it this side discrete memoryless source. Similarly, this is discrete memoryless channel. What is the meaning of discrete? You understand, discrete means it has finite size. That is what we are sending and what we are receiving, they are in discrete form, not in continuous form. And memoryless because what we are receiving here is dependent on the particular input only. For example, if for x0 we are receiving y0, then y0 depends only on x0 and not on x1 or y2. So that is the meaning of memoryless. So if it goes through this channel, and at this point the alphabet that we receive is y. Let's say this is y0, y1, and this is up to k minus 1. Okay. Obviously, as in analog communication, you know where noise is added. In analog communication, the main factor for noise addition is the channel. If your message is going through air or through copper cable, everywhere noise, the most of the noise that is added is at this point, that is in the channel. Similarly, here also we will have noise. So y is the noisy output of x. Clear? That is, along with x we add noise, and so we get y, this output here. Okay. So this is the representation of discrete memoryless channel. You understand it? Clear? So what we actually do to eliminate or at least reduce error, we actually eliminate. We are able to eliminate it. We are able to eliminate the probability of error to a very good extent. So to do that, we take this output, we encode it as per the channel. That is called channel encoding. And then that passes through the channel, and at this end, first of all, we have a channel decoder. Then we have source decoder, and then we get the message. So this is an introduction to how digital communication works. Okay, now we'll introduce some terminologies that you should understand. The first term that we'll be understanding is called transition probabilities. Transition probabilities, by the name itself, it's clear. Transition probability means what we get related to what we send. So it's written like this: P small, and we have Y, K was associated with Y by this X, J. This is transition probability. This is the characteristics of the channel. Transition probability. Okay. So this is given as this. It is expressed as P capital Y. This is the alphabet of the channel, equal to YK, and this is X alphabet XJ. It's written like this. Now obviously this is probability, therefore we'll have two properties. First is it will lie between 0 and 1. We know this very well. The probability of Y getting Y when this X input is given. So the transition probability YK XJ, it lies between 0 and 1 because this is probability. This you should keep in mind. Second is, you know, if for one input, if we have 0 to k number of output probabilities, then obviously if you add them all, that is k equal to 0 to that much, you'll have this PYK for particular input will be equal to 1. So these are the two properties of this. This is called transition probability. You should keep this meaning and you should keep this definition. We'll explore this further now. Now from here, a very convenient way of describing a discrete memoryless channel, because we are now exploring memoryless channel, discrete memoryless channels. So how to express a discrete memoryless channel using transition probabilities? What we do, we get a matrix that is called channel matrix or stochastic matrix. It's given like this. It is a matrix given as PY0 X X0. This is when X for Y0 for X0. Then here what will our Y will keep on increasing. That is second probability will be Y1 for X0. Similarly, you can go on up till this will be YK minus 1 from 0 to K minus 1, so that the total number of elements is K. So this will be for X0. Meaning is, these are the transitional probabilities related to X0. That is, you send X0 and you receive Y0. You send X0, you receive Y1. You send X0, you receive this one. Similarly, you receive Y0 while you send X1. You receive Y0 while you send X2. This is a very crude language to express that you send and you receive. We are talking of probability. Probability, transitional probability of Y0 with respect to X2. So this goes on up to the last term, that is Xj minus 1. Okay. So this way, you know how this will proceed. Finally, what you will get here? The last term will be P will be Yk minus 1 and Xj minus 1. Okay. So this is called channel matrix for discrete memoryless channel, DMC. So this is called channel matrix or also called stochastic matrix. I know this won't be giving you any insight. You won't be getting what I am trying to convey. But have patience. We'll see examples and then you will understand what is the meaning of this. Okay. So this is for a channel which has j number of input variables or input elements, symbols, and k number of output symbols. So for this we have this j into k matrix. If we have binary, we'll have 2 into 2 because there are 2 inputs and 2 outputs only, 0 1 0 1. So there will have 2 1 2 1 2. So this much only. So this is a generalized form of that matrix. Okay. Now there is a term called joint probability distribution because x and y both are random variables. So there is a term called joint probability distribution. You must have studied this. If not, just try to understand this. It is represented like this. X we have j number and y we have k. We have used j for x and y, that is j number of symbols. So it is expressed like this. This is x equal to xj and y equal to yk, or it can be written as this: y equal to yk by x equal to xj into phi of x equal to xj. That is, in terms of probability, in terms of conditional probability, this is written as p yk xj into probability xj. What is this? You know, this is conditional probability. You must have studied conditional probability. If not, go and revise what is conditional probability. So joint probability distribution of the variable x and y is this, which is actually conditional probability y xj p xj. Okay. So if you have to find for the term 1 y1 x1, so you will take probability y1 by x1 into probability of x1. If you have forgotten, you should go to that particular chapter, conditional probability, and see what is the meaning of this and how we find probabilities. For now, for the time being, you should remember this, that joint probability distribution of the random variables x and y is given as this. Okay. We saw discrete memoryless channel matrix, that is stochastic matrix, and we saw what is joint probability distribution. Let's see binary symmetric channel, that is of utmost importance because our communication is binary, digital communication is in binary. So that is called binary symmetric channel. Binary symmetric channel. You'll be asked in your exams also. This is a very important question. We'll be explaining this channel, and as and when our study goes deeper and deeper, we'll keep on adding new parameters to this. So for the time being, we are just defining what is a binary symmetric channel. See, binary symmetric channel, the input can be input alphabet that will be x0, that is 0, and x1, that is 1. So we have two elements only. This is not the way to write. You should write 0 and 1. 0 and 1, that is x0 equal to 0 and x1 equal to 1. Okay, and we have the output as 0 1, simple, that is y0 equal to 0 and y1 equal to 1. Let's say it said like this: the conditional probability of error. Let's say the conditional probability of error is p, that is the chance of flipping, because 0 can be 1 or 1 can be 0. This is the only possibility. So if the term is called conditional, you should learn this: conditional probability of error. So if this be p, what is the meaning? That you send 0 and you get 1, or you send 1 and you get 0. So let's say this is conditional probability of error. So let's say this is x0 equal to 0 and x1 equal to 1. So first is you send 0 and you get 0. Obviously, if this is p, then this will be 1 minus p, and you send 0 and you get 1. So what is the meaning? This is probability P, that is, this goes by probability P. If this P happens, then you'll get 1, the bit will be reversed. Similarly, this is 1, and if you send 1 and get 1, the probability is 1 minus P, but you send 1 and you get, say, 0, so this will be P. Okay, so we'll have a figure like this, that is a diagram like this, and we want to see the channel matrix. So channel matrix is, if you remember, y0 by x0 first. So y0 by x0, what is the probability? This is y. So y0 when x0 has been sent, that was the first term. So that is 1 minus P. Y0 by, I am talking of this, y0 when x0 was sent. So this is 1 minus P. Then what was this? This was y0 when x1 sent. This y0 when x1 sent. This one is this, and what is the probability? It is P. Okay. Now second one, what was it? It was, we get y0 when what has been sent? X1 has been sent. So x1 has been, this is the input and this is the output. So probability is P. And the other one, that is 1 1. That is, you send 1 and you get 1. 1 minus P. Okay. So if you see this, you will get channel matrix. If this is still not clear to you, I am writing like this. Let's say, let's do this once again. This was Py0 when x0 has been sent, and this was Py0 when x1 was sent. This is Py1 when x0 has been sent, and this Py1 when x1 has been sent. This is channel matrix. I defined you in the last board only. So what is this? You send x0 and you get y0. What is the probability? You send x0 and you get y0. The probability is 1 minus P. So I am writing 1 minus P. Now see, getting y1 when x0 has been sent, y1 when x0 has been sent, the probability is P. So this is P. Now getting y0 when x1 has been sent, y0 when x1 has been sent, see, this is P. So this is P, and getting y1 when x1 has been sent, 1 minus P. Clear? So this is actually, it has the probabilities of transition, this channel matrix, that is transition from input to output. What is the probability? So if you have the stochastic matrix or the channel matrix, you know, if I send this input, what will be the output? That is, what is the probability of getting this output? To get y1 when x0 has been sent, what is the probability? That is transition probability. Clear? That I am sending, let's say this was 1 and 0 binary. If that is a decimal system, I am sending 1 and I am getting 2 at the output. So what is the probability? That is called transition probability. That is sending 1 getting 2, sending 1 getting 1, sending 1 getting 3. These are transition probability. So this, I think now what is the meaning of transition probability you understand. And when you plot or when you map it in a matrix, that getting any element, you can understand what we send and what we get. What is the transition probability between the two symbols, yk and xj? So that you can find from the channel matrix. So this is channel matrix. Okay, and this is represented here. What you see in the matrix, you can easily see it here. This is a diagram. So this diagram is called transition probability diagram. So the usefulness of this diagram is that just looking at it, you know that if I send 0, I get 1 with a probability P. That is the transition probability of getting 1 when 0 has been sent is P. The transition probability of getting a 0 when 1 has been sent is P. The transition probability of getting a 0 when 0 has been sent is 1 minus P. Similarly, Transition probability of 1 when 1 has been sent is 1 minus p. So this is a visual diagram. A diagram gives you a visual statement of what the process is. So this is called transition probability diagram, and this is a channel matrix. I think this is now clear to you. So this binary symmetric channel, the basic understanding you have now. Later on we'll understand several concepts, and we'll develop those concepts with respect to binary symmetric channel, BSC. Okay, what is a binary symmetric channel? That is clear to you. Now we'll try to introduce you what is mutual information. Now start with this. You know what is H of S, that is entropy, that is the average information content per symbol, that is HS. So what is HX? HX is if you have this alphabet, okay, and you have x0, x1, x1, x2 up to xj minus 1. If this is your alphabet, the source alphabet, or not source but source to the channel. I explained you from source we do source encoding, and that output is our input to the channel. So if that is this alphabet X, and these are the symbols. So X is a random variable, that is it can be x0, it can be x1, it can be x2. So you know what this is the entropy. Here we define conditional entropy. This is the entropy of X. Here now we define a term that is called conditional entropy. I am writing it here, conditional entropy. What is the meaning of conditional entropy? Conditional entropy for given y, that is if our, let's say this is the output alphabet y0, y1 up to yk minus 1. Okay, so let's say we are talking of y1. For y equal to y1, what is the distribution? X is random distribution, you know. So this is conditional entropy, that is entropy of X for a given y1. So when we are talking for a given yk, y equal to yk, this is conditional entropy. Hx was entropy of that alphabet X, but Hx given y equal to yk is conditional entropy for a particular symbol yk. This is defined as, in terms of probability, it is given as X, this we are talking of X. So j equal to 0 to, let's say, j minus 1. We have from 0 to 0 minus 1. This is P of xj yk, that is conditional probability of X for given y, into log, obviously base 2 because we are talking of binary, 1 by the same thing. If you remember, our information was basically p log 1 by p, that is minus p log p. So it's same here. The difference, only difference is this is conditional probability, that is conditional probability for alphabet X for a given y equal to yk is j equal to 0 to j minus 1. This is conditional probability xj given yk log to 1 p xj yk. Okay, so you should remember this expression by heart. Clear? This is called conditional entropy. And what is the meaning of it? It means the average amount of uncertainty. Here we are not talking of information. We are saying when we are talking of conditional entropy, we mean the average amount of uncertainty that remains when the output has been observed. We see the output y, y0, y1 up to yk minus 1. So what is the uncertainty? Still what uncertainty remains with the input? This quantity actually explains that average amount, that is per symbol. Clear? So we define conditional entropy as the average amount of uncertainty remaining about the channel input when the channel output has been observed. Okay, the average amount of uncertainty remaining about the channel input when the channel output has been observed. This is the definition of conditional entropy. Okay, so what we have learned from this conditional entropy, that this entropy relates the channel output y to the channel input x. If we say hx, it gives the entropy of the channel input itself. But when we say hx by y, conditional entropy, we relate the output with respect to the input x. Okay. Now we introduce a term that is called mutual information. A very important term in digital communication, that is called mutual information. We write it like this: I x semicolon capital alphabet semicolon y. This is mutual information and it is defined as hx minus conditional entropy hx y. Okay, so the point to understand is, what is hx? Hx means the uncertainty related to the channel input before observing the channel output. That is, if this is your this alphabet x, then before observing this output we have this set of output. Okay, so we don't know what this output is, so the uncertainty associated with this is represented by hx when we don't know what the output is. And in similar terms, this is what? This is the uncertainty of the input of this when this has been observed. Clear? Both these terms represent uncertainty about the channel input x, both this and this. These two represent the uncertainty associated with this alphabet input. But this is when we don't know about this, we haven't observed what the output is. Then what is the uncertainty? And this is when we have observed this, what is the uncertainty? So this is the meaning of hx and hxy, that is the conditional entropy. So then what is the meaning of this mutual information? It is the measure of, now this is talking uncertainty about the channel input. This is measure of the uncertainty of the channel input after resolving the channel output. Clear? This is uncertainty with respect to this. This is uncertainty with respect to this. But this is when we don't know about y. This is when we know about y. This is measure, that is how to calculate, or I'm writing measure of uncertainty, not uncertainty, measure of uncertainty of this channel input x after resolving the output y. This is the definition of mutual information. Clear? This is mutual information. Okay, and this can also be expressed like this, that is, this is defined with respect to the input. You can also write it like this: h of y when similar, this is the output when input has not been observed, and this is the output when input has been observed. So this is the measure of uncertainty of the channel output when the input has been resolved. Uncertainty of the input has been resolved. So this is the definition of mutual information. So let's see what are the properties of mutual information. The mutual information of a channel is symmetric. This is the first property. Property 1 is that mutual information is symmetric. That is, as we just saw, I x y is equal to I y x. That is, you see from the input to output or output to input. So first property is it is symmetric. Second property is it is non-negative. Non-negative, that is, this x y is greater than 0. Okay, so it is non-negative. Information is this or this is greater than or equal to 0. Clear? Non-negative means it can be equal to 0. And when it will be 0? This will be 0 when the output and the input are statistically independent. So we have this information equal to 0 when output and input are statistically independent. Statistically independent. Okay. Now the third property of mutual information is, firstly, what is joint entropy of? We have defined joint entropy of x and y. X and y, it is basically equal to from j equal to 0 to j minus 1, from k equal to 0 to k minus 1, and this is p xj yk log 2 1 by p xj yk. Okay, so this is hxy, joint probability of the two random variables x and y. And the third property of mutual information is that mutual information is related to the channel input and channel output entropy by this expression, hx plus hy minus hxy. And what is hxy? Joint entropy, and joint entropy is this. So this is the third property of mutual information. So somewhere you may require this to get the values for symmetric channel. For binary symmetric channels, this is very easy. We have only 2 inputs and 2 outputs. So this will be, there will be 4 terms only. So that won't be very difficult to get. Okay. So the relation between mutual information and joint entropy. This is the third property.